tutorial, we're going to solve the internal forces of a beam with a UDL, that is, a uniformly distributed load. We're going to start off with the simplest case, that is, a simply supported beam with a UDL that spans the whole of that beam. So let's look at what we're going to solve, find the reactions, find the internal forces, and summarize. Let's go. So this is the beam that we're going to solve. It's a 9 meter span beam. It's got a pin support at A, it's got a roller support at B, and it's got a UDL of 12 kilonewtons per meter, spanning the whole 9 meters. The first thing we're going to do is we're going to draw our free body diagram and find the reactions. We'll start off by replacing the supports with the actual reaction forces. So let's start off with A. At A we had a pin support, so that means that I've got a vertical force of AY and a horizontal force of AX. And at B we have a roller support, so I'm just going to replace that with a vertical reaction force of BY. We're just going to go systematically through forces and then moments just to understand how the UDL behaves. So starting off with a sum of forces in x equals 0, I've got AX and don't have any other horizontal reaction forces or forces, so AX equals 0. I'm now going to move on to forces in Y, with this being my positive Y direction. So here I've got AY plus BY, and then I have the force from the UDL, from the uniformly distributed load. Now for any distributed load, the force, the resultant force from that load is always going to be the area under that load. So for us here, we've got a load that is rectangular. Its height is 12 kilonewton per meters and its length is 9 meters. So this area is going to be equivalent to the resultant force. So minus, because it is going down, 12 kilonewton per meter times 9 meters. And we can see that kilonewton per meter times meter is going to give us kilonewtons, so that is going to give us force. And that whole thing has to equal 0 because there's nothing else in that vertical direction. Okay, so just a reminder, this is the resultant force, RF, and that equals the area. And if I sum of all of this up, I get that AY plus BY equals 108. And now I'm going to move on to moments around A, with this counterclockwise being my positive direction. And I've got a positive moment from BY, so plus BY times 9, because that's the distance. And then I'm going to have a minus or a negative moment from the UDL, so minus. And this is going to be the area, which gives me the force, so the 12 times 9. And I'm going to locate that resultant force at the centroid of the shape. Okay, so whenever you have a distributed load, it doesn't matter what shape that distributed load is. The area of the shape gives you the force, and the centroid gives you the location of that resultant force. In our case here, it is going to be the centroid of a rectangle, which is in the middle of the rectangle, and this is where we're going to put our resultant force for the purpose of calculating the moments around A. So the area, 12 times 9, that gives me the force. And then the distance here is going to be in the middle, so it's going to be 4.5 meters from each side. So in this case here, times 4.5 meters, and that is the distance. And that all equals 0. Worth just checking units. So the force we already said, the 12 kilonewton per meter times meter gives me kilonewtons, and the distance gives me meters. So kilonewton meters exactly the units I'm expecting to get for a moment. So that works out as 9by equals 486. And if I divide that by 9, so that gives me by equals 54 kilonewtons. And what I can do now is I can go back to this equation here and say that AY equals 108 minus BY, which means 108 minus 54, and therefore AY equals 54 kilonewtons. And the very last thing that I need to do here is replace those forces that I've drawn, AX, AY and BY, with the actual values. So let's start off with AX, that worked out as 0, so we can ignore that. AY worked out as 54, so let's replace that here. And BY also worked out as 54, so let's introduce that here. So I hope that was clear. The main takeaway from this is whenever you have a distributed load, the area under the distributed load is your resultant force, and the distance, when you want to calculate moments, is used by finding the centroid of that shape. And now that we've understood that, we're ready to go and calculate the internal forces. So, as you know, whenever I want to calculate the internal forces, what I like to do is I like to draw underneath the actual free body diagram with the reaction forces, space to find my axial load, my shear force, and my bending moment diagram. And that's really helpful because it allows me to just step by step fill in these graphs and see also what is the correlation between shear and moment. Let's start off by deciding where we're going to cut this beam. Now here I can see that the minute that we've passed the support, we have this UDL started, and that UDL is consistent, so it really doesn't matter. I'm just going to have to cut my beam somewhere along it, somewhere between A and B. So let's do just that. Let's draw our beam out. This is my little segment of the beam. I've got my reaction force of 54. I've got my external load of 12 kilonewton per meter, and I've got my distance x starting here, and x in this case is going to be between 0 and 9 meters. Okay, so one cut for this entire beam. I need now to draw in my internal forces. That is what is keeping everything at equilibrium. So I've got N, I've got my shear S, and I've got my bending moment M, all drawn in the directions of my sign convention for positive. Starting off with the axial load, so sum of forces in X equals 0, and I've got this axial load that I'm looking for, the internal axial load, and nothing else, so that works out as 0, and that is going to be pretty easy to draw onto my diagram. The next thing I'm going to do is my sum of forces in Y equals 0, and in this case I have got my S going down. So sorry, this is my positive direction, so S is going down, so that's negative. And then I've got my 54 going up, my reaction force, and then I've got my UDL, okay? So my UDL is going down, so that is negative, and it's always going to be that area of the rectangle, and the rectangle is always going to be 12 times X, right? It doesn't matter where along the beam I am. If I'm at 1 meter, that's 12 times 1. If I'm at 2 meters, it's 12 times 2, and so forth. It's always going to be 12 times that distance that I've passed. Okay, and equals 0. So that means that my S equals 54 minus 12x. And there might be a few places that I'm interested in. What happens, for example, at the support, right? So what happens when x equals 0? What happens in the middle when x equals 4.5 meters? And what happens at the very end when s equals 9? So when x equals 0, I can see here that I get 54 kilonewtons, which is exactly what I'm expecting, because when x equals 0, I've got my reaction force of 54, and that distributed load hasn't really kicked in. So 54 is good. When I am at 4.5 meters, I've got 54 minus 12 times 4.5, and that works out as 0. And when I reach the other end, I've got 54 minus 12 times 9, and that works out as minus 54, which also makes sense to me because I've reached the other side of the reaction. So let's first draw in what I know, and then we'll move on to the moments. So in terms of the axial load, I'm just drawing that in, but we said that was just a line of 0. In terms of my shear force, I started off with 54. I then, in the middle, went through 0, and then I became negative 54, and that is just a straight line between them. And the last thing that I need to do is my moments. I'm just going to move down a little bit. So my sum of moments around the cut has to equal 0. So around the cut, I've got my moment that I've exposed, so mx, which is giving a positive moment. And then I've got minus 54 times x, so that is my reaction force times the x. And then I've got my UDL, and my UDL is going to be a positive moment. It's going to be the area first, that's the force, so 12x, that is the area, which is the force. And then the distance is going to be, if we imagine putting that resultant force at the centroid of the shape, it's going to be at x over 2. So times x over 2 equals 0. Okay, so just to show you what I mean, we've got our UDL. The distance is x, whatever that x may be, something between 0 and 9. I've calculated the area, and I'm putting my resultant force at the location of the centroid, which is going to be x over 2 from the edge of the shape. And rewriting that, the moment equals 54x minus 6x squared. And once again, I'm going to check a few interesting points. So I want to know what happens when x equals 0, when x equals 4.5, so in the middle of the beam, and what happens when x equals 9, so at the end of the beam. So when x equals 0, it's pretty easy to tell that that's 0, which is exactly what I'm expecting to happen at the support of a simply supported beam. When x equals 4.5, I've got 54 times 4.5 minus 6 times 4.5 squared, and that works out as 121.5 kilonewton meters. And when x equals 9, I've got 54 times 9 minus 6 times 9 squared, and that works out as 0, which again is what I'm expecting at the support. My question now is, what side do I draw that? So I've got 0 here, I've got 0 here, and now I've got 121.5. Do I draw it here on the top? Do I draw it here on the bottom? Let's figure that one out together. So this is my beam. I assumed that the moment went like that. It did indeed come out as positive, which means that this is the correct direction, which is pulling at the bottom and pushing at the top. Pulling is tension, pushing is compression, and I always draw on the tension side. The other thing that I want to note here is that I can see in my equation that I've got x squared. Okay, So this means that this is a parabola, okay? So I know that it's going to be a curved shape, and so it has to go like this, okay? With this being my 121.5 positive moment drawn on the tension side. So let's just have a look at a few of the things that we found here. So now that we found our internal forces, before we finish off, let's just have a look at some of the key things that we found while we were using UDLs. So let's just look back at our drawings and the equations we found. So looking here, let's just stress a few things. So the first thing that I want to stress here is that this was our equation for shear, and this was our equation for moment. And we can see there's a connection between them. The first thing is the shear in this case has an x, right? It's a function of x. So this means that it is linear, as opposed to our moment, which we just found was a parabola. The second thing we want to see is that when our shear passed through 0, so this point here, this was where our maximum moment is, here. And those things are very important, and they are apparent once we learn what the connection between shear and moment is. You might already be able to spot this. But those are a few important things to pay attention to. Let's just zoom in one last time to have a look at the results for a beam under a UDL. And that's it. We've successfully solved a beam under a uniformly distributed load. Next step will be to look at some distributed loads, so not necessarily uniform, and then to mix them up with some concentrated loads and perhaps even concentrated moments. So I hope you join me next time when we try to tick something off that list. Bye for now.